Welcome back to Applied Physics. In this video, I want to talk about weight. The idea of weight is more technically correct to call the gravitational force. The weight of an object is the force with which gravity pulls on the object. And that's a lot of where the biggest confusions in translating between the US customary and metric units comes into play. In the US customary system, we measure weight in pounds. Pounds are a measure of force. In the metric system, we measure mass in grams. If we want to talk about a force, we use newtons. So translating between pounds and grams or pounds and kilograms is really nonsensical in most applications. We should be translating between pounds and newtons. That's kind of waved away in the situation that we spend most of our lives in, which is on the surface of planet Earth. Because on the surface of planet Earth, there is a constant gravitational acceleration of 9.80 meters per square second. And of course, by Newton's law, we know that force is mass times acceleration. These are vector quantities. I should probably put vector hats on them to make sure that that makes sense. And the acceleration of gravity is gravitational acceleration, obviously. So I'm going to be calling this F sub g, force of gravity. And F sub g is simply equal to mass times gravitational acceleration, and it's always oriented downward towards the center of the Earth, the way you expect a force to work. If you're not on the surface of the Earth, the acceleration of gravity can change. Newton's law of universal gravitation is a little bit beyond the scope of this course, but it is a thing, it exists. We could figure out gravitational accelerations in other contexts, but we're going to stick with the tried and true Fg equals mg. All right. So we can do a simple example asking, something like, what force is acting on a 100 kilogram person standing in the middle of the room? Well, the obvious force acting on this person is the force of gravity. So let's ask about a force of gravity. Of course, if we want a force of gravity, we need to know gravitational acceleration. It's still 9.80 meters per square second. And we need to know the mass of this person, which is given to us as 100 kilograms. Notice the decimal point in that number 100 telling us that all of those zeros are significant. And then we can multiply our 100 kilograms times 9.80 meters per square second. That gives us 980 kilogram meter per square second, and a kilogram meter per square second is a Newton. There's a natural follow-up to this question that you may or may not have thought of previously. If there are 980 newtons of force pulling us down onto the surface, if we are accelerating downward at 9.80 meters per square second, why are we not falling? The answer is at once obvious and kind of difficult. We're not falling because our feet are solidly on the ground, right? A person standing in the middle of the room like I am right now, my feet are firmly on the ground. I can feel all of this force pushing on my feet. I can feel the pressure in the soles of my shoes, but I'm not moving. And mathematically, that has to be because there's another force counteracting that force pulling me downward. That other force, why is scrolling not working today on this? I'll figure that out later. For now, let's just continue onward. And talk about the normal force. There are two things that we need to know about the normal force. First of all, the normal force is the name of the force that prevents things from falling through solid surfaces. And the second thing we need to know is that the normal force always acts perpendicular to the surface in question. So, if I am talking about an object on an inclined plane, like the side of a hill, and we have some object that's sitting there, well, the gravitational force is going to pull downward. But the normal force is going to work in the normal direction or perpendicular direction to the surface. So it doesn't quite counteract 100% gravity. Right? Normal force is not just the opposite of gravity, it's a little bit more involved than that. But in the simple case of a horizontal surface and an object sitting on top of the horizontal surface, gravitational force is going to point downward. Normal force is going to point upward. And in that simple case, the normal force is just going to oppose gravity. In the more complicated case, there's a lot more going on. We're not going to get into any calculations of that sort. But with that, we can say very simply, for that 100 kilogram person, gravity pulls downward with 980 newtons. The normal force pushes upward with 980 newtons. All right, so let's take a look at an experiment. I'm going to go ahead and set up a table. On that table, I am going to put an air track, right? A frictionless, one-dimensional object. I'm going to attach to that air track a pulley. I'm going to put a cart on the air track. Let's go ahead and say that this cart has a mass of m1. I'm going to attach a string to the cart. I'm going to loop it over the pulley and then let it fall down here where I have it attached to some counterweight. Let's call that counterweight m2. Without doing any calculations, just with your experience in everyday life, you should be able to predict what's going to happen. Right? The mass of the counterweight is going to pull downward, and that's going to cause the cart to move towards the pulley. Depending on the relative masses of the cart and the counterweight, the rate at which the cart is going to be pulled towards the pulley is going to change, but it's still going to be pulled in that direction. And that's kind of the important thing. If this was just on the table surface, there might be enough friction between the cart and the table to prevent it from moving if the masses are disproportionate enough. But I'm putting this on an air track, so there is no friction, there's nothing to worry about in that regard. And the question is very simply, what is the acceleration experienced by the cart? Well, in order to answer that question, we do need a couple of other pieces of information. Let's go ahead and figure out what these masses are. I'm just going to go to some clear space so I have plenty of room to write this out. There we go. All right, so the acceleration is the unknown. I'll put a nice question mark there. We're talking about gravity, so we probably need gravitational acceleration, 9.80 meters per square second. And then we need to know m1, which was the mass of the cart itself. And let's go ahead and call that 225 grams, or 0.225 kilograms. And then we need to know the counterweight's mass, m2, that's the hanging mass. And let's go ahead and call that 25 grams. So that's 0.025 kilograms. And that's really all we need to know. From that information, we can figure out, well, the cart itself, if I scroll back up, the cart itself has gravity pulling downward, but it also has a normal force pushing upward, which are going to counter each other. I don't need to worry too much about what's happening there, so I'm not going to. Let's just focus on the things that are going to make a difference. Right? There is definitely going to be a gravitational force pulling downward on this counterweight. That force is going to get transferred into the string and cause everything else to be pulled as well. If I assume that the string is massless and inelastic and the pulley is massless, then there's nowhere for the force to escape except going to these two objects. Right? If the pulley had a mass to it, then we'd have to worry about how fast is it spinning, what does it take to get it spinning. If the string had mass to it, we'd have all sorts of worries to have to think about. But let's assume that the pulley weighs or has a mass much less than a gram. Let's assume that the string has a mass much less than a gram. By making those assumptions, it's going to make everything easier and it's going to make the problem solvable. All right, so we have a force. It is going to be the gravitational force acting on the hanging mass M2. Helps if I write down the right mass. Right, mass 2 is 0.025 kilograms. Acceleration of gravity is 9.80 meters per square second. And so in total, the force acting on this is 0.245 newtons. Right? That is the only force that is causing acceleration. Again, yes, there is gravity acting on the cart. There is a normal force acting on the cart. Those two forces are canceling each other out. They're not causing any acceleration. So this is the only force we have to worry about. But this force is not causing acceleration just to the counterweight or just to the cart. It's causing acceleration to the entire system. So we're going to need the total mass of the system. I'll call that big M. That's just going to be M1 plus M2. So we add 0.225 kilograms plus 0.025 kilograms, and we get 0.250 kilograms. All right, with that, we have the information. I'm running a little bit low on space. Let's come back over here. And Newton's second law, F equals mass times acceleration. And here we'll take the entire mass of the system, the counterweight and the cart tied together. Technically, we should also include the mass of the string here, but we just said that the string is going to be massless. It's a negligible amount. Adding it doesn't change the calculation in any way, shape, or form. Less than the 1 gram of significant digits we have. All right, so our force is 0.245 newtons. Our mass is 0.250 kilograms. And A is the thing that we're trying to solve for. So rearranging here pretty simply, 0.245 newtons divided by 0.250 kilograms is going to give me the value of A. And if I punch that into my calculator, I get 0.980. And remember, newtons is kilograms times meters per square second. So when we divide by kilograms, that will leave us meters per square second, which is the units we expect as our acceleration. So in this particular configuration, we should expect just shy of 1 meter per square second as the acceleration experienced by the cart and counterweight system. All right, I think that's probably good enough for this video, so I'll wrap up with that. As always, thank you for joining me, and I'll see you next time.